Um, thank you very much for the opportunity to speak in your seminar. Yes, I'm going to be talking about random walks on definable sets and particularly anti-concentration of those random walks on definable sets. And the theme of the talk is basically going to be that every anti-concentration result we have for concentrating on a single point can be bootstrapped up to a much more general setting. So let me set up a model of a random walk. So suppose I have some vectors, v1 through vn, inside r to the d. So these are going to be non-random vectors. They're going to be vectors of your choice. They're going to define this model of a random walk. And the random walk that we're going to take based on these vectors is going to be very simple, where for each of the vectors, we're either going to walk forward or backwards in the direction of that vector. And we're going to do each of these steps independently. So epsilon 1 through epsilon n is going to be a uniformly random sequence of signs. So plus minus the n, uniformly random. So this model of a random walk where we take n independent steps in and different directions. There's been a lot of study on, well, let me tell you what people have studied about it. But the broad setup that I'm going to take is that we have this random walk and we just have some subset of r to the d. So let me just show you, for example, let's say we start at the origin. There's a 50% chance we walk backwards and a 50% chance we walk forward. And this random walk does n steps. And if we're lucky or unlucky, we end up in some particular region of space that we're interested in. And the following two questions, which were, I guess, the first one was initially asked by Littlewood and Offord back in the 30s, was what is the best upper bound on the probability that the random walk lies inside S, which is independent of the choice of vectors. So you want a uniform estimate for this probability. And that's useful because if you have a uniform estimate, that means that you don't really need to analyze your random walk much in order to get just like a first upper bound to understand this. And in particular, for example, as n goes to infinity, you might ask a qualitative question like, does this probability go to 0 as n goes to infinity? And if it goes to 0, how fast does it go to 0? So that's kind of what we're asking in this first question. And the second question is the inverse question, which asks if this random walk happens to concentrate very highly on this set. So if this is large, then what can we say about these steps? What can we say about these steps? Does it imply some kind of are they highly structured? Or is it possible to get a high concentration on a set, even if your vectors are kind of randomly chosen? So these are the main questions that I want to focus on today. And the classical results that people have looked at have been in the setting, for a good reason, that all of the vectors have a lower bound on their step size. So, well, there's a lower bound on the size of the steps of your random walk. So people have studied random walks with large steps. And in asking, what region should I ask this question about? Well, voluminous regions, they're like contained inside balls and they contain balls. So kind of the universal region to ask this question for would be a ball. So knowing this question for a ball would imply it for all other voluminous regions to some extent. And the classical results are first that the probability of concentration of this random walk in the set, regardless of how you choose the vectors, first goes to 0 as n goes to infinity, but actually goes to 0 quite quickly as n goes to infinity. it actually goes to 0 at polynomial speed for fixed d and r being the radius of this ball s. And we actually know the asymptotically best constants by work of Frankel and Ferretti. Best constants. So this result is nothing to sneeze at. Even getting n to the -1/2 with non-optimal constants took about 40 years from Littlewood and Offord in the 30s to Erdős in the 50s to Kleitman. Daniel Kleitman ultimately came up with the notion of symmetric chain decomposition that allowed him to show that that actually goes to 0 at this specific rate. And then in the 90s, Frankel and Ferretti determined these constants. So, we have the best possible information about the probability that you end up in this ball. For the second question, what structure can we say about the size of the vectors if the probability is large? We also have best possible results. So culminating work of Nguyen and Vu, which built on work of Tao, Nguyen and Vu, says that if the probability that this random walk is inside the region is large, then almost all of these vectors Vn lie in a rank 2C, rank 2C, generalized arithmetic progression. With side lengths, with side lengths n. So it's not like a crazy big arithmetic progression, but okay, it's a rank 2C generalized arithmetic progression. And this result was actually important in establishing some of the first non-trivial upper bounds on the probability that a random matrix, for example, a random 0-1 matrix, is singular. This turned out to be a key input in the last step of this derivation. And there have since been more applications of this inverse result. And of course, people in this additive combinatorics seminar know that inverse results are very important. So this has had lots of applications beyond just the initial application of random matrices. So let me give an example to show why this probability goes to 0 with speed n to the -1/2. Or I should say, let me give an example of some vectors which achieve this bound. I'm not going to prove the bound. I'm just going to show you like what the extremal case is that causes the answer to be n to the -1/2. So here I have, a point, and here I have a ball. And my goal is to create a strategy that gets this random walk to lie inside this ball with the highest possible probability after the random walk terminates. So it turns out that the best strategy, up to this multiplicative constant, is the following. You take your first step to bring you right into the center of the ball, V1. And, maybe you succeeded and maybe you failed, but there's a 50% chance you succeeded. So, let's just say you succeeded. Let's, pray that we succeeded on the first step. Now I'm in the center of the ball, and I want to remain as close to the center of the ball as possible. To do this, I'm going to choose some vector v, any fixed vector that I want, and I'm going to take v2 through vn, the next n-1 steps, to all equal this fixed vector v. So what's going to happen is, assuming I succeeded on my first step, I'm going to do a one-dimensional random walk where I walk forward and forward and backward and backward and forward and backward and backward and forward. And I'm going to hope that I just end up right back where I start. So the probability that you're contained in the set is going to be, well, there's a half chance that you succeed on the first step. And then you need exactly half of the remaining steps to go forward and half to go backwards. So there's going to be n-1, choose n-1 over 2 successes, over to the n-1 possibilities. And I was probably way too careful about this because now I'm going to eat up all the constants in this little squiggly notation, that this is approximately n to the minus 1/2 up to some constant. So n to the minus 1/2 here represents the median of a binomial distribution. It represents the odds that if I do a one-dimensional walk, I do exactly the same number of forward steps as backward steps, and that allows me to stay as close as possible to the origin. What these inverse results are saying is that if you deviate from this strategy, so the contrapositive of this inverse result is basically saying if you deviate from the strategy enough, then you are going to start deviating faster than you would by just doing a one-dimensional walk. So this is somehow the best possible thing that we can do. So that's the complete story. We know everything about this question, basically. But what I want to ask is the following question that I'm going to pretty quickly shut down, but this is going to be the motivating question for the talk, so it is what it is. Is the lower bound on P of X and S an upper bound? Is the lower bound, no, this is, wait, a lower bound on P of X and S. No, so this is an upper bound with the big O notation. And this is saying if you're concentrated highly, then you concentrate in a high rank arithmetic progression. The contrapositive would have a less than or equal to. It would say if you aren't in a low rank arithmetic progression, then your probability of concentrating in the set is very small. So does that answer that question? Great. So we're going to ask what happens if we do not require these steps to have size at least 1. So why did I say everything in the context of all the steps having size at least 1? Well, the example I gave hasn't really, shown that yet. What's going to happen if we don't require all the steps to have size at least 1, so we allow arbitrarily tiny step sizes, is that there's going to be some way better strategy than the one I gave that's going to make this probability insanely high rather than going to 0 with probability n to the minus 1/2. So let's see that. So problems with this. So if S is a ball, so let's just take the example we have before. Under this assumption that I can take arbitrarily tiny steps, I can take my first step, again, to get to the center of the ball. But now I have a much better strategy than just choosing some fixed vector and going forward, backward, backward, forward. You just have to take all of your other vectors to be tiny. You take them to be much smaller than the radius of the ball. And if you do this, if you take all of your vectors to be really, really, really small, so I'm saying we see our set S, and then we choose our vectors. Well, the vectors are allowed to be chosen so tiny that they don't influence at all where this random walk ends up going, then the whole probability of lying inside this ball is going to be entirely what happens with the first step, which is going to be 1/2, which is a total disaster. This doesn't go to 0, doesn't go to 0 at any rate. We can actually choose these vectors so that the probability is actually a positive constant, regardless of what n is. And the reason is we can exploit the tininess of the vectors to completely just destroy the spirit of the question. This question doesn't really capture the essence of what we were trying to do before. So that's a little bit of a problem. And really, this problem, if I was to refine it, this would happen whenever S contains a line segment. So if S contains a line segment, then you would take your first step to the center of the line segment and all of your other steps to be extremely small in the direction of the line segment. And again, the probability that your walk ends up in the set is entirely determined by the success of this first vector ending up in your segment. So, you know, we're kind of dead in the water here with I guess these two classes of sets, you know, balls and sets that contain line segments. So let's, you know, see, I guess, what class of sets have we not ruled out? So if it doesn't contain a ball, that means it has to be like lower dimensional, because kind of the definition of being full dimensional means you contain balls. You have to be like a surface inside space, and you can't contain a line segment, so you have to be kind of wiggly, I guess, in some other sense, but you can't be too wiggly. So here's the third way that you could potentially have a problem. If your surface was very wiggly and happened to contain, I don't know, the graph of y equals cosine of x, then there's a unique additional problem that can occur, which is, so your surface contains this graph. And here's where you start. I can take my first vector to bring me right onto the graph, then my subsequent vectors to be in the period of the graph. And again, only the first vector affects the outcome of this random walk lying in the set. So not only do we have like infinitesimal issues coming from the tininess of the sets, if I allow unbounded sets, which, you know, I'm putting no restrictions on S, I'm really trying to find just any class of sets that works. If we allow unboundedly large sets, then we also have global problems to deal with. We have infinitesimal additive structure and global additive structure that are coming to bite us. But there's a bright side. So the bright side is that there are some sets for which, you know, you can actually show that the probability goes to 0, and it goes to 0 at this polynomial rate. For example, I guess you could take a single point. So you could take a single point, and I claim that the probability that you end up exactly on that point is n to the minus 1/2. This actually follows formally from the ball concentration result by treating the point as like a really, 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 really small ball relative to the sizes of your vectors. There's a little bit more disappointing than that, because this is actually, this doesn't actually capture the dimensionality of the problem. So this is actually secretly a one-dimensional phenomenon, because if I was in d dimensions and I happen to have some brilliant choice of vectors that concentrated very highly on some point, then if I just project everything down to the real line, then all of the probabilities stay the same. So this has nothing to do with the high dimensionality of space. This would also hold in like the real, this also follows from just the one-dimensional result, or even the result in the integers, for which in both cases, Erdős has a lovely argument to show that this probability happens. So you lose the geometry entirely. Like space doesn't really have a purpose in the setup if you take a point. But okay, what other sets can we do it for? I guess you can do it for a finite union of points. So that's something by the union bound. So X and S. But the more points you take, the worse this constant's going to get. If you take these points in an arithmetic progression, then actually the constant goes up proportional to the number of points. So this constant now depends on the number of points, and you know, as the number of points goes to infinity, this gets worse and worse and worse and worse. So obviously, if I have infinitely many points, this constant would be infinite, and you wouldn't get any result. Except this happens to not be true. So Kevin Costello, in one of his papers on the Littlewood-Offord problem for bilinear forms, showed, if you read his argument carefully and optimize it, that the probability that X is an S is big O of n to the minus 1/2 if S is a parabola. So you can actually show that if your set is a parabola, then you get the same upper bound as you get for a point. And this is surprising because if you think about what this is saying, so let's imagine we start adding like landing points for x on this parabola. So I have like 1 point, 2 point, and 3 point, and 4 point. Then the probability that this random walk lands on this one particular point, or these 2 particular points, or these 3 particular points, this is going to, the constant is going to get worse and worse and worse. But at some point, after like 10 or so points that I have on this parabola, this probability is going to start to stabilize. And as I add more points on the parabola to allow this random walk to lie on, it's not actually getting the constant in front to be better and better. And in fact, even if I add countably many points or uncountably many points, something about the geometry of the parabola is preventing this constant from exceeding a certain universal threshold. So I was very excited about this result, and together with Matthew Kwan and Jacob Fox, we generalized this result. We also got an inverse theorem for this result. So here's our theorem. So if S is a definable set, I'll tell you what definable means in a minute, but it will include a parabola and pretty much every set you would ever want to write down in R to the D, not containing any line segment, not containing any line segment, then we have answers for 1 and 2. So first, the probability that this random walk lies in the set is, okay, so when D is 2, we recover Costello's result, and the constant obviously has to depend on what the set is. So this matches exactly what you would get for concentrating on a point. And I'm saying that the fact it was a point was not really important. What mattered was that it was definable in the sense that I'm going to tell you in a moment. So you get the same result for a point concentration as S concentration. And when D is at least 3, unfortunately, we can only get n to the negative 1/2 plus little o s of 1. So the exponent approaches the correct thing as n goes to infinity. And really the only thing stopping us from getting what we believe to be the correct upper bound, which is this, would be to get sharp estimates on the number of rational and algebraic points on transcendental surfaces of bounded height, which is a long-standing open problem. And also we'd have to entirely resolve the Gotsman lineal conjecture for Boolean functions, which is also a long-standing open problem. And we don't know how to do either of those things. There were like 2 bottlenecks, and we were like, nah, all right, this is what we got. So this, you know, we can't do better than this at the moment. So we can get the exponent to approach the correct thing. But already getting the exponent to approach the correct thing requires like a lot of, there are a lot of steps required to show the correct exponent. It's definitely using a lot more theorems than you would think to reduce it down to there. And we also have an inverse theorem. So the probability, yeah.
How does that square with your example of the cosine curve?
Because definable will explicitly avoid cosine. That's the only function you learn in calculus it'll avoid.
Cosine is not definable. Okay.
Yes. We'll see what definable means. But yes, cosine is not defined. Excellent question. Then our other theorem is that if the probability is at least n to the c, then you get exactly the same theorem. So I'm not like omitting any hypotheses here. I'm just like writing it in the same way for comparison. So if the probability is at least n to the minus c, then almost all of the vectors lie in a rank. I can't remember what the exact thing we optimized it down to, but it's some multiple of this constant that doesn't depend on the set. Generalized arithmetic progression, So your vectors have to be very structured in order to concentrate on anything, literally, well, other than cosine, literally anything. but I should probably stop beating around the bush and actually say what definable is. So a subset is definable if there is a formula, phi of x1 through xd, such that S is equal to what I'm going to call S phi, which by definition is the set of all x1 through xd, which make this formula true. So for example, if the formula was y equals x squared, this would define a parabola. But now I have to tell you what the formula is allowed, since obviously I'm not going to allow cosine of x, where phi is allowed the following things. So what is this formula going to have to look like? Well, I'm going to allow you things like real numbers, variables, brackets. Not a lot so far. You can write like open bracket 3x, close bracket 4. So not great. Let's give you a little bit more power to create more interesting functions within the formula. So here's what I'm going to allow you. I'm going to allow you plus, so you can create linear things. That's pretty good. Times, you can now make polynomials. You can now make x squared, for example. I'm also going to allow you like exp and log. Those are free. So that's nice because everyone likes exp. And also, if I give you any analytic function of R variables, if you restrict it to a compact domain, so this is going to be from a neighborhood of 0, 1 to the R to R. If you restrict it to a compact set, I'll let you have it. So I'm not going to allow you cosine of x, but I'll allow you cosine of x restricted to 0 to 2 pi. So for example, so the leaves of cosine of x aren't the problem. Like the individual lobes aren't causing the issue. It's the infiniteness of cosine of x that's causing the issue that I said before. But geometrically, like the arc of cosine of x is fine. But okay, so we have functions, but functions aren't true. We need to have predicates that make them true or false. So less than, equals, and greater. So now we can make true statements like y equals x squared. And I don't really want to restrict you in what you can write down. So let's just throw in like every logical connective, whatever, etc. All that. So now you can make like, I don't know, boolean combinations of any sets you can possibly write down in the entire world. I'll give you just a little bit more freedom just because, sometimes writing down a set is kind of annoying. So let me also give you for all. You can quantify over the reals, and you can also existentially quantify over the reals. So you can talk, for example, about where a set is continuous or differentiable, since these have epsilon delta definitions. They go, for all epsilon, there exists a delta such that yada, 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 yada. So this ultimately doesn't give you that many more sets that you can write down. It gives you something slightly stronger like sub-analytic sets rather than analytic sets. But it's just nice to know what you're allowed to do without breaking the rules of this formula. So yeah, just any formula like this, you write it down. If the set doesn't contain a line segment, then the theorem applies. So for example, y equals x squared was such a formula. And also you can just write down random combinations of symbols. And that'll be, so you could write down just some random formula. You can go and with some other random formula, equal to 0. And you can go or with some other random formula. So for example, I could take, I don't know, x squared plus y squared equals plus z squared equals 1. So that's the definable set. So just basically stuff you want to write down. Don't use unrestricted sine and cosine, and you're good. Okay, so any questions about that before I come to the key definition that kind of controls how bad these sets are? Okay, cool. So here is the key definition that I want to give. And this definition bridges between additive combinatorics and geometry in a way that works incredibly well with definable sets, which is good because sets that aren't definable, you can kind of manufacture to make the question fail. So definable sets it's kind of good that it works with sets for which the theorem is true. So here's the definition. I'm going to define a notion called additive dimension. I'm going to write it dim plus. The additive dimension of S is equal to K. And I'm going to say it's of complexity C. So there's actually an additional parameter here that's going to come into play. So there's going to be a dimension to the set, an additive dimension. There's going to be some complexity parameter that gets carried along with this definition. If the following holds true. So when K is 0, the definition is just going to be that S is finite, and the number of points is in most C. So the complexity is literally measuring the complexity of this finite set in terms of like how many points, how many like coordinates I need to describe it. When K is bigger than 0, it's going to be a little bit of a mouthful. It's going to say that we can take our set, we can break it up into pieces. So I take my initial set that I claim has dimension K with this weird notion of dimension, break it up into a bunch of pieces. And each of these pieces has the following irreducibility property, that if I intersect two distinct translates of one of these sets that I broke the thing up into, this has lower additive dimension, again of complexity C. For all I, and for all two distinct translates inside part of the D. So what is this definition doing, and why am I claiming that this definition is going to allow us to bridge between like finite additive combinatorics and like these complicated geometric sets that lie in space? So let's see, for example, what this definition says when C equals 1. So when C equals 1, it turns out that this definition, so here you don't break your set up at every stage, you just always repeatedly take your new set and intersect it with a distinct translate. This definition is actually saying that S does not contain a sum of K plus 1 two-element sets, V K plus 1, W K plus 1. So it does not contain any sum of K plus 1 two-element sets, which would be like a pretty good, first definition of like a discrete set in an abelian group having a certain dimension. You could think that this is like a discrete analog of a K plus 1 dimensional parallelepiped, because this is like the sum of the endpoints, I guess, of the parallelepiped. So this is morally K plus 1 dimensional. So we're kind of saying that S has dimension K if it doesn't contain anything K plus 1 dimensional. But that's a little bit too weak if you think of like having a robust notion of dimension, because that notion has some problems. For example, like if my set was literally just the disjoint union of all of these points, it was literally just these two, the K plus 1 points, then its additive dimension would be very high. But that's a terrible thing for a dimension to have. So this definition is basically forcing the fact that the dimension of a union of two sets, if I ignore what the complexities are, this is the maximum of the two dimensions. This is like kind of the unique way, this is the like freest way of fixing that problem with the most obvious way you would define a notion of a dimension based on avoiding K plus 1 dimensional objects in a discrete setting. But related to that, actually, so this definition fixes this obvious problem that the most obvious notion of a discrete notion of dimension would have. But also this definition does not use topology. This definition only uses the group structure on R to the D to define. It doesn't use topology at all. Topology isn't actually entering this equation. So actually, this is an entirely combinatorial definition that is ultimately trying to capture a geometric concept. Like before I said that it only uses the group structure, feels like I'm doing something geometric. But I'm actually not. Everything here can be described entirely just with respect to the set inside this abstract group R to the D. So this is a genuinely combinatorial definition. And the motivation for this breaking up into a bunch of pieces, so I don't want to go into this too much because otherwise I'd go over and I don't want to go over. But the idea is that if S is defined by polynomial equations, then this decomposition into the individual pieces, this is the decomposition into irreducible components, And if you do the decomposition into irreducible components, then you can take the additive dimension to be at most the actual dimension. So you can show with actual like Euclidean dimension, if you use the decomposition into irreducible components. So if like S is a union of these two things, the components are like circle and parabola, and you run this definition, you get that there's a uniform bound on how many sets you need to break up in every step. And the uniform bound that you get actually follows from something called Beizut's theorem. So we actually show definable sets satisfy basically this particular aspect of Beizut's theorem, that it controls how complicated intersections can be. And that's like the main like idea. Model theoretically is we extend Beizut's theorem to definable sets to allow us to show that not only do sets defined by polynomials have this property, but really just any sets you want to write down. If you can repeatedly break it up, self-intersect, break it up, self-intersect, and there's some uniform constant that bounds the complexity of this like decision tree, regardless of like what I guess translates you choose inside R to the D to do this at each step. So any questions about that? Cool. So let me do some combinatorics because everyone likes combinatorics. Let me prove for you that this definition has some bearing on the question of random walks lying on the set. So here's the claim is that if the additive dimension of your set is at most K and you're of complexity C, then the probability that the random walk lies in the set is bounded by some constant multiple of, and I'm going to write down something weaker than the theorem that we ultimately prove, because basically to go beyond this theorem, you need more ideas from model theory to overcome this. But just this theorem that you get some polynomial upper bound on these sets with additive dimension K is what I want to show. So the complexity is only going to affect this constant in front. It doesn't affect this exponent, which is good because, you know, if the exponent only depends on the actual dimension of the set, well, it depends on the additive dimension, but we show, so we show that the additive dimension is at most the dimension for S definable. So this actually gives like the exponent doesn't depend on how terrible your set is, only the constant in front does. So how do we prove this claim? Well, we need one lemma from probability theory, which I'm going to call the decoupling lemma. And it's going to say the following thing. Suppose I have some independent random variables y and z. I have any event which depends on the outcomes of those two independent random variables. Then the probability of this event occurring is at most the probability that the event occurs, and the event also occurs when I resample the second part of the event raised to the 1/2. So this is an independently resampled z. Resampled z. So this is saying concretely that this event and this event are positively correlated. This is a positive correlation for any event. If I resample part of it, then those two things are positively correlated because each of these has probability of occurring. So this is literally just a correlation estimate. And this is Jensen's inequality for f of x equals x squared. So the proof is like 1 line. Okay, so let's prove this claim, and let's prove it when this constant is equal to 1. So I'm going to go back to, I'm going to like scroll back to the definition when I actually need to use it, but it's going to happen at one specific point in the proof. And I'm only going to prove the claim when c equals 1, but the proof for any c is the same. Okay, so what is this proof of this claim? So we're going to induct on k. Induct on k. So when k equals 0, S is going to be a finite union of points. And this is going to be that Littlewood-Offord result for a finite union of points. So this for k equals 0, actually for any c, this is just the result I said before, that concentrating on a finite union of points is only so complicated, only has probability n to the -1/2 of occurring. Okay, so that's the base case. Now I want to apply this decoupling lemma, but I have a single, my event is that x lies in S, which is not anything depending on two variables. So we're going to break x up into two parts, y and z, where y is the first half of the steps and z is the second half of the steps. So a random walk has the self-similarity that's made up of two random walks. And now I can write down an event which depends on two random variables, y and z, independent of each other, which is very important. So let's draw a picture of what we have so far. So I was looking at the odds that x lied in this walk, and I broke it up into two things, y and z. So we apply this decoupling lemma. So the probability that you end up in the walk is, well, it's the probability that y plus z is in the walk. So nothing interesting there. I apply the lemma, and it says that if I resample the second part of the walk, then up to this exponent of 1/2, we can estimate by the probability that both of these things occur. So this is what I'm actually going to estimate, is the probability this branched walk lies inside the set, and I'm going to raise it to the power of 1/2. Okay, so here comes the clever part. Here comes the one clever part of this proof. This is the probability that y, so now I wanted to just a y to lie in something. What is this condition saying y lies inside? Well, it's saying it lies inside the random set s minus z cap s minus z prime. So it's the first half of the walk lies in the random set s minus z cap s minus z prime. But now let me refer back to the definition of this definition that I had before. So this definition, at least when c is 1, so I don't break s up, so s is equal to s1. If I intersect two distinct translates, the dimension drops. Well, this notion of dimension drops, and the complexity stays the same. So it's exactly designed to make it so I can now apply the inductive hypothesis to this part of the set. So this is dimension at most k minus 1 of complexity. Well, I guess I'm doing the c equals 1k, so it's complexity 1. So you apply the inductive hypothesis. So this is O of n to the minus 1 over 2 to the k, the 1/2. This depends on k, which is n to the minus 1 over 2 to the k plus 1. So that's the proof. So it's this one idea that the whole walk, this whole branched walk lying in the set is the same as saying the first half lies inside a random set for which I have information about by the inductive hypothesis. And like, yeah, so that's all I'll say about it. So that's the like key combinatorial idea that allows us to use this definition to prove something interesting. But now let me tell you about the other side of this. So let me tell you about what's special about this collection of functions that I wrote before. So a collection of functions. So this collection of functions, f. So this is going to be basically what happened at this stage when I wrote down like this giant collection of functions. What's special about them in this definition? Well, what's actually special about this collection of functions is a very particular property called O-minimality. And that's actually the only thing that's important about this collection of functions. So this collection of functions is O-minimal if, when you stick it into the definition of a definable set, and you look at a definable set of the real line, then this is always a finite union of points and intervals. A finite union of points and intervals. The intervals can be open or closed on either end or infinite. So saying the O-minimality is saying that definable subsets of the real line are very nice. And that's it. That's the only thing that's needed in this about these functions at all. So Tarski a long time ago showed this property for addition and multiplication. He showed that real semi-algebraic geometry, there was a quantifier elimination algorithm. That's the content of the Tarski-Seidenberg theorem. It shows real algebraic geometry is nice in some sense. And Van den Dries and Miller were two logicians who showed the result for this complicated collection of functions I wrote before, which includes exp and log and all these other restricted analytic functions. So, okay, so I just have this definition. This seems like kind of a stupid definition because it's not really imposing a lot of restriction on these functions or on the definable sets, it seems. But let me tell you some facts about O-minimal sets. So first of all, this is not some crazy model-theoretic, like, you know, Cantor set, crazy set theoretic, large cardinal craziness. These sets are actually the nicest possible sets. So all of these definable sets are a finite union of, let's say, connected k-smooth manifolds or k-differentiable manifolds. So actually, there's no pathologies here. This is the opposite of pathology is implied by this definition of O-minimality, which is kind of weird because the definition doesn't say anything about differentiability. And here I'm pulling manifolds out of the air from this definition, which only refers to, you know, points and line segments. So that's surprising. And now what's wrong with cosine of x? Well, we look at those x where cosine of x is equal to 1. This is an infinite discrete subset of the real line. So cosine of x is excluded because it creates an infinite discrete subset of the real line. Okay. So that's why we don't allow cosine of x, is because this definition explicitly precludes us from having periodic structures. So what I wanted to do is tell you about, let me see. So let me maybe tell you the key theorem that is the kind of black box that you want to use when working with O-minimality. So the black box theorem is, suppose we have some definable set, or I guess the order of operations is there exists some function from the naturals to the naturals such that the number of connected components of a definable set is at most this function of the number of symbols in phi. So this, which I guess you could call the complexity of the formula, is the analog of degree for algebraic sets. So let me give you an example theorem that has a very short proof that uses this theorem as a black box to prove something interesting. So let's say that we have one of these definable sets inside R to the D, which has no line segments inside it. Then let's show that it doesn't contain unboundedly large arithmetic progressions. So S phi does not contain any arithmetic progression of length m. So this is like one thing you need to show about the boundedness of the additive structure of your set, is that it doesn't contain unboundedly large arithmetic progressions. Otherwise, the theorem would be false for the same reason it was false for sets that contain line segments. So here's the proof. You let n be the number of symbols in your formula. And you say, for any y in R to the D and any vector in R to the D minus 0, we're going to consider a new formula, psi. So what's this new formula going to be? It's going to be phi, the formula phi. And then I'm going to add on to it the words, and there exists a t such that x1 equals y1 plus tv1, and dot, 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 and xd equals yd plus tvd. Right. So this is the new formula. Let's let T be the subset where this formula is true. YV is true. So when is this formula true? Well, it's true when both of these clauses are true. So it's true for the set that we're interested in. And it's true for this weird clause, which exactly cuts out the line y plus tv. So this set here is a subset of a line. So it's a finite union of points and intervals, points and intervals. But we explicitly excluded the possibility of intervals. So this is actually a finite collection of points. So last line of the proof, the number of points of S of T is the number of connected components of T, which is less than f of the number of symbols in this formula. So how many symbols are in the formula? Well, there's n symbols that I used here, and then, I don't know, 1000d. So here's a crude upper bound of the number of symbols that I used, and I call this m. So actually, we showed the stronger statement that any intersection with a line only has at most m points, which in particular implies that every arithmetic progression has at most m points. So that's all I want to say. And if you have questions, you can ask me